Okay, welcome to this week's lab, 1D Motion. This is just an intro video to kind of get you comfortable with the equipment that we have and the goals for the lab and what we'll be doing. So to get right into it, what we have equipment-wise is a track, which you can see along the top are two strips of tape with white and black marks on them. We have a sensor, the black thing on the end of the track, which connects to this white box, which connects us to the laptop we have here. So what happens is on the bottom of the cart, we have these two holes with photodiodes behind them. And what the point of those are is to detect the difference between a light and a dark stripe on the track. And so through these sensors and tracking how long the cart is moving, we can, it can give us, basically by counting, position, and then with the time it runs, also velocity and acceleration. So how this works is the cart runs along the track. The photodiodes detect change between light and dark, and so how many of those that pass lets it calculate a distance, and how fast they're passing helps it to calculate a velocity and eventually an acceleration. It then beams the data to the sensor on the end through a little infrared diode here, which the computer then tracks and gives us a graph, which is really handy when you want to compare graphs of position, velocity, and acceleration. The key point about using this, though, is that you want to make sure your cart is on, so the blue light is on, and that it is facing the sensor. So you want it to be on the track, facing with the sensor side, so the dark gray side of the cart should always be facing the sensor. So then what we're going to do is run through an example of moving the cart around so you can kind of see on a graph what that looks like. So for our purposes, the sensor is 0 position. And so I'm going to hit collect here and move the cart away from the sensor. And as you can see, as it moves away, position increases. While it was moving, since I wasn't touching it, you can largely see that the velocity remains fairly constant. And except for where I push it and stop it, you actually see a constant acceleration of 0, more or less. And so that gives us an idea of the motion. But the key point to take away from this is as it moves away from the sensor, you can see the position is increasing. So it started at 0 right up against the sensor, and it ended up at about 1.5. And then similarly, if I do it again and move it towards the sensor, you can see the position does in fact decrease. And so that's what you should be thinking about as we go forwards through the examples in the lab itself, is how this graph of position relates to the actual position of the cart, and then also where you push the cart or the cart hits something like the sensor at the end of the track. Those are not the interesting parts of what we're doing. We're concerned with the parts of motion. So after we've given it a push, we want to know what happens. And then we want to know up until before it hits the sensor or you stop it with your hand. So we're largely interested in this constant velocity section, not the before and after where we pushed it and it stops by hitting something. So keep that stuff in mind as you go forwards. What we're going to have you do is move the cart, or watch the cart move and make predictions based on the motion you observe. And then we're going to have you run it with the graphing software going, and we want you to compare your predictions of what the position, velocity, and acceleration graph should look like to the actual position, velocity, and acceleration graphs that you get from the program, and then hopefully resolve any inconsistencies that you have between them. So any biases or previously held beliefs about how the motion should look, and hopefully resolve inconsistencies between that and what it does actually end up looking like. So that is the end of the intro video. Moving on, you'll be doing the experiment itself, so good luck, and I hope it goes well.